Hi, and welcome to Going Big with Containers. My name's Matt Callanan. I'm an engineering manager and tech lead at Expedia in our cloud acceleration team. So we exist to help speed up the lives of developers, and our mission is to make developers' lives easier and faster when it comes to deploying to the cloud, migrating out of data centers, and beginning their cloud journey. So I work out of our Brisbane, Australia office, and out of Brisbane, we focus on the ECS cluster management, the deployment automation aspects of our cloud platform. So in this presentation, I'm going to focus on those aspects of deploying to the cloud with Docker using ECS. I'm not going to talk about data center connectivity using Direct Connect. I'm not going to talk about the persistence layer and the various database options that our teams can choose from. Those are out of scope for this conversation. I'm going to be focusing on how do we really scale when it comes to using containers for deploying applications to the cloud. So you've probably heard of Expedia. It's a large enterprise with a number of different brands under their umbrella that you might also recognize. So we're going to look at a number of the building blocks that make up our platform deploying to the cloud there. We're going to start with the application creation side of things. How do we generate microservices? How do we make that easy for our teams to get microservices up and going? We'll talk about deployment automation when it comes to deploying to ECS, how we do that. And we'll look at the underlying management of those ECS clusters, how we manage the underlying EC2 infrastructure. And it's all built on top of AWS. There's a whole bunch of different services there that we use. I'm not going to go through those in details, but they're all part of our platform. And ultimately, we rely on AWS support when it comes to drilling into specific issues and recommendations. So to start with, application creation. What is the cost of creating a microservice? So if you had an experiment that you want to run in isolation out in production, you've got some ideas, how long will it take you to get your experiment out there? And what will you need to do? So you'll need to create a source code repository, a working code base. You'll need a basic test suite. You'll want to deploy to immutable servers using infrastructure as code that dev and ops can maintain with centralized logging, centralized monitoring. You want chat notifications. You want a load balancer. You'll want some sort of CNAME, DNS, networking. You'll want blue-green deploys, a continuous delivery pipeline. How long is all that going to take to create? You want to get your experiment out there. Is it a couple of days? Is it a week, a month, 6 weeks? I think a month is generous for a lot of enterprises. Let's say it takes 2 weeks. What's the opportunity cost? What could you have been doing in the 2 weeks that it takes to generate that microservice and to go through that experience? How much context switching was going on for your development teams? How much rigorous discussions were there between your developers and your admins, fighting once again about naming standards and all the different approval processes that you need to go through, all the yak shaving. And these are all things that prevent experimentation and innovation. And in terms of what we call the time value of information, a piece of information today is worth more than that same piece of information tomorrow. So if we say that every commit that a developer makes is a hypothesis, I think this change, this commit that I'm making will result in better sales or improved performance or less bugs. Then how much could having that information today be more beneficial to your company? This is what DevOps, continuous delivery, and lean and agile all teach us, is that feedback is king. We need feedback as fast as possible, and that really helps us to get the results from our experiment. And the less risky your changes become if you can get the feedback the fastest possible way. So we internally within Expedia, we've created a microservice generation platform. We call it Primer. And teams will go to the internal Primer tool, into the UI, and they'll click a button, I want to create an app. And they can choose from a number of different templates, some JVM, Drop Wizard, Spring Boot templates, some Ruby-based templates, Python, PHP, Scala, whatever's been created by the internal community will be available to the developer. They'll go through a series of processes to create the application, the Docker image, and the builds. And within 10 minutes, they'll have an application repository for their microservice with a continuous delivery pipeline ready for commits, a Docker repository. The application will be built as a Docker image and deployed to a prod-like testing environment. So within 10 minutes, they can get started with their experiment. All those things that could possibly take you 2 weeks or a month to do within an enterprise. Our teams within Expedia do this 20 times a day. Every business day, there's 20 new microservices created. Just because the cost is so low that people can easily make an experiment and say, I want to test out this particular idea that I have. You might be wondering what those distracting spikes are. Hackathons, people getting excited about hacking away on some new ideas. So going back to the question, how long does it take to create a microservice? If it takes more than a few days to go through this process, all the approvals and everything, then your teams are unlikely to consider even doing this. The time burden's too great, and it's a big opportunity cost that's been lost there. And when it comes to getting feedback within a monolith, if a monolith has like a 2-week release cycle, and with a microservice you can get it out within a day, that's a 10x release cycle on your monolith. What could you have been doing in those 2 weeks? What other experiments could you have been running? And within our industry, fast feedback is so important because over 2/3 of our experiments fail. 2/3 of our projects, we have a 68% failure rate within our industry. And so if you have a 10x cycle time, you're 10 times less likely to be able to get the results from your experiments. So in the time that you could have run 10 experiments with 3 successful experiment attempts out of that with microservices, you could have run 1 failed experiment in your 10-week-long monolith release cycle. Does your feature even belong in your monolith? Probably not. It probably started out looking nicely, a beautiful architecture, but then over time more and more features were crammed in there, and your new experiment doesn't really belong there. You're just increasing the technical debt. So the benefits that we see out of Primer is twofold. We've got the reduction in cost due to experimentation and fast feedback, and we get the benefit of speed from that as well. In terms of deployment automation, so how do we get our containers onto the cloud? We're going to look at the deployment pipelines, auto-scaling, security, logging, traffic management. What's the motivation? Why did we choose to use containers for our microservice platform? Why not VMs? Why not functions with Lambda? And we do have these offerings for our Primer platform. Teams can choose to use dedicated EC2 instances with CloudFormation. They can choose to deploy to Lambda. But containers really provides the sweet spot of a nice, consistent deployment packaging mechanism that's very portable. Developers can run the same Docker image on their laptop as they can run on an ECS cluster, and they can port it between different types of deployment topologies. It also gives them the flexibility of resources and CPU and memory, which you don't see as much flexibility with something like Lambdas. Lambdas are great. They provide that extra level of abstraction. You just deploy the code, the function, but then you're restricted in terms of memory and CPU and execution time. And then at the other end of the spectrum, dedicated EC2 instances with dedicated VMs gives you even more flexibility with CPU and memory, but then you're constrained, your application's constrained to the operating system that it's running on, whereas Docker abstracts it away for you. So the default for most of our templates with Primer is to build a Docker image and deploy that to ECS. And then when it comes to clusters, so the clustering technology that you'll see with containers, there's various different technologies out there. You've got Kubernetes, you've got Mesos, Docker Swarm, ECS. They're all very similar technologies. And what they provide is the brain, the scheduler, which you tell the brain, I want to deploy this Docker image. I want 4 copies of it for this application, and the brain works out where in this pre-built fleet of VMs should I put that workload to balance it out across there. And so that's the benefit of having a clustering technology. You don't need to work out how am I going to get my Docker image onto a VM. The brains takes care of that for you. Why did we choose Amazon ECS? Why not some of the other offerings? Amazon ECS integrates nicely with things like IAM, with load balancers, with auto-scaling, and for AZ balancing, so you get redundancy across AZs. People ask, are we scared about lock-in with Amazon? We're on Amazon anyway, we're on ECS, we're on AWS anyway, so that it's not really worth it trying to abstract across multiple different clustering technologies. The time and effort that we would spend in there, we're better off just getting benefit from one technology, so that's where we are with that. In terms of some of the statistics of our footprint on ECS, we have 2,600 ECS services deployed. So an ECS service is what we'd call an application. 1,100 of those are unique applications deployed to clusters all around the world. We have 13,000 containers across 860 instances. That's across 13 different ECS clusters. The green is production, the blue is test. Our largest production cluster is 480 applications, 230 instances. They're across 11 different VPCs in 5 different regions. This is a visualization of one of our production clusters. So the vertical bars there are instances. Each instance has eight cores of CPU. Each of the colored boxes is a task. And now a task in ECS is a collection of containers. So if I say I want my application to run 4 times in parallel on this cluster, then you'll have 4 tasks. So the similarly colored tasks belong to the same service. And this is using our C3Viz open source tool that you can download from expedia.com on GitHub. In terms of the deployment pipeline, so fairly typical. You'll get your Git repo that's created by Primer for you, which has your source code and your application config. When a developer does a commit to the Git repo, it will trigger off a commit build. We'll use Jenkins for that. The commit build will compile the code, do basic unit testing. We'll build the artifact as a jar, a war, a zip, whatever artifact makes sense for that technology. And then what it will do is pull in a base Docker image that we've built ahead of time. So for all of our Primer templates, we have a base Docker image for each of those that's built ahead of time. So we'll pull in that base Docker image, and then it will layer on top of that image by copying in the artifact that's been built and generate a new application Docker image and push that to the internal Docker registry. And then after the commit build is successful, it will trigger off a test deployment build, which will deploy to ECS. And we've set up the ECS cluster ahead of time as well, and I'll discuss the management of those clusters in the next section. So the deployment tells ECS to pull down the application Docker image from the Docker registry and pull down the application config that's specific for that target environment. And then teams can choose to go to other testing environments as well, integration or stress environments. When it comes to deploying to prod, it's a very similar process. They will trigger the build to go to production, choose which region they want to go to, and that will pull in the exact same Docker image and pull in the application config that's specific to that environment. And then teams can choose to go multi-region if they want. That's just separate builds. And we provide a pipelining tool on top of this that's internal to Expedia as well, which drives Jenkins that says each team can choose, when a test deployment's finished, I want to automatically go to production, but maybe I only want to do the deployment, not the release, and that will stop at deployment so they can do testing, and they can insert various automated testing phases within their pipelining tool. And so they can build up a fully automated pipeline, or they can build up semi-automated. It's really up to each team to choose what they want to do. And when it comes to deploying to ECS, we split down the deployment phase and the release phase. And what that means is that we want to allow a way for teams to test their container is working in the target environment before they send live production traffic to it. What that looks like is this. So they have a service already running, their application's running on version 1 in ECS. The 4 boxes there represent 4 tasks, each running its own copy of the container that they've built. That service will be behind a load balancer, which is behind a Route 53 CNAME. We want to go to version 2. So what we'll do is create a separate ECS service called the Canary service, and we'll deploy a single task just for testing. That's going to be on version 2. It's the exact same application, but a newer version of the image. That's behind its own load balancer and its own Route 53 CNAME. And teams can begin testing against that Canary. When it comes to, we call that the deploy. And then when it comes to release time after they've tested their deploy, we use the Amazon's ECS update service command, which says, okay, take this live running service and do an implicit blue-green deploy on there. And what that does is basically treats it like an implicit blue-green deploy by saying, I'm going to create all replacement tasks, the green tasks there, and then you've kind of in mixed mode there. You've got both version 1 and version 2 running behind the load balancer. And then once version 2 tasks are successfully placed behind the load balancer, it removes the old blue tasks, and then you're running your live service purely on version 2. And then we go ahead and delete the Canary. So that's how we do blue-green deploys on ECS. For application autoscaling, we take advantage of the autoscaling feature that's built into ECS. And so we can say, when this application reaches 70–75% of CPU utilization, then go ahead and spin up an extra 2 tasks. And so that will just create another 2 tasks and put them behind the load balancer, and it happens seamlessly to the user. And then it can scale back down when after the peak load has kind of died down, it can scale back down to the containers that it had before. For role-based security, we use IAM. So when an application is deployed, it gets a minimal set of IAM roles, permissions. But teams can choose to say, I want this application to be associated with a specific role. And it uses the IAM ECS task role to do that. And that allows teams to say, for this particular app, I want to access these AWS services, and only that application can have access those permissions. For logging, we use Splunk. So how do we get logs from a container onto Splunk? So on the left is the ECS, a single ECS task is represented. So we saw a service there with 4 tasks. This is a single task. And within a task, you can have more than one container. So we'll have the main application container. This will be maybe your Java web service maybe running on here. It might be whatever technology you've chosen as your applications running on there. And we'll deploy alongside that what we call a Splunk forwarder container. And this is using what's known in the industry as a sidecar container pattern. So every application container has its own Splunk forwarder container there. And the executable, the web service that's running on the container, and the Splunk forwarder has its own binary that's running on there. And so when the executable is writing out logs to disk, it's simply shared using a volume sharing mechanism between the containers on that same task. The Splunk binary sees those logs being written and simply forwards them to Splunk, and the user can see those on the Splunk server UI. And then the executable might also log to standard out and standard error, which is a process that we prefer. We try and aim for 12-factor apps where you're not writing to disk, but some apps do both. And when it writes out to the console, we simply use the Splunk logging driver, which comes with Docker, and ECS can plug into that. The traffic management. So we have the picture here of an application stack with the ECS service, the load balancer, the Route 53 CNAME. Let's say that that's running within a particular region. We'll call it application A. How does internet traffic get to our service? Traffic's coming through on the internet. We have an internal team that just does traffic management, and they've defined some software that you can set up some traffic rules so that when traffic's coming from the internet, you can say, all right, this application only needs to be in a single region, so we'll send all traffic from the internet to that particular CNAME for that application. But maybe you want to go multi-region, which is a preferred approach. In that case, we can set up some geo rules to say, well, depending on where you are in the world, go to the closest region for you. Intra-region. So if you're within one region with multiple apps, how do they discover each other? So perhaps application A is in region 1, application B is also in region 1, but it's in a private subnet. For app A to talk to app B, simply the application just uses the Route 53 CNAME. That's a pretty simple kind of setup. If we have 2 public apps, app A and app C, and they want to talk to each other, again, just use the same mechanism. That covers off the deployment automation section. The benefits that we see there is the speed aspect of reducing a lot of manual steps down to basically a single click or even a fully automated process via our pipelining tool. And then there's the safety, because those steps have all been automated. It's a repeatable and reliable process that has very little manual intervention. So for cluster management, we're going to look at how we do the creation of our clusters using immutable servers and auto-scaling, how we do zero downtime upgrades of those cluster instances, how we do monitoring and right-sizing. So in terms of creating the ECS cluster, we start off with a CloudFormation stack that has an auto-scaling group. We'll start off always with 5 instances. That just gives us enough redundancy when it comes to deploying and releasing applications. And then those auto-scaling groups are set to automatically scale out based on demand of that particular cluster. And we'll create the ECS cluster separately to the CloudFormation stack. And when those instances start up, when they launch, they'll automatically join the CloudFormation, the ECS cluster that they've been configured to join. via the launch configuration in the CloudFormation stack. And then the auto-scaling rules we've set up there, so once you hit 70% CPU reservation across the cluster, add an instance, 60% memory, and scale down for 10% CPU or 20% memory. Those statistics, those metrics have been set just based on our experience over the years. And we use an immutable server approach when it comes to creating and updating our instances. So by immutable server approach, I mean that if we need to make any changes to the instances, changing the configuration or updating packages, we will not do that on instances in place. We will simply replace the entire instance. Not only is this industry best practice, but it's something that we've learned through bitter experience. You don't restart Docker on all of your instances simultaneously. You don't do that more than once accidentally. So what we do is we build a golden AMI, and we'll version it, and we'll use a new version of our new AMI to roll out updates to all of our clusters. So how do we build that AMI? What we do is we take the ECS optimized AMI. So the Amazon ECS team, they produce an AMI whenever they have updates that they want to bring forward. Their updates might include, they build theirs on top of the Amazon Linux AMI. So it might be a security update to Amazon Linux that they want to incorporate. They put the Docker daemon into that image, and they put their ECS agent, which is just a small Docker container that does the communications between what's running on the EC2 instance and the scheduling brain within the ECS service. So they may have updates to either of those that they want to apply. When they build a new ECS optimized AMI, we'll take that and we'll create a temporary instance out of that AMI. And on top of that, we'll layer down our standard Expedia image, our standard configuration by a chef. And we'll put down the configuration for Docker that we want to have on all of our clusters everywhere in the world. So we'll take that temporary instance and bake a new AMI out of that. And then we'll make that AMI available to all regions and all accounts that we want to create and update clusters in. Then when it comes to launch time, when an auto-scaling group needs to launch a new instance of that AMI, it's got all of those things already baked into that new instance. And at launch time, we have a custom bootstrap script that runs that configures the instance for that particular cluster in that particular environment and region. And that bootstrap script includes the ECS cluster configuration. What cluster should I join? That changes depending on which region you're in. We control the startup lifecycle of the ECS agent itself. We want to make sure that that agent doesn't start until we've fully configured the box. And also the Docker configuration, we control when the Docker daemon starts up. The bootstrap script also initiates some cron jobs. So every minute we'll check that the ECS agent and the Docker daemon are still running. If not, we'll restart them. We'll push some custom metrics. So is the ECS agent running? Is Docker daemon still running? And we'll push those metrics to CloudWatch and various other CloudWatch metrics so that we can monitor the state of the instance. And so we have a fair bit of experience when it comes to upgrading these clusters. So we had a few different attempts over the years on how to do zero downtime cluster updates. So when it comes to updating a production cluster, if you have a cluster with 100 instances in it and you want to replace all of those, you need to be very careful about making sure that all the containers on those 100 instances safely move to a new 100 instances. And so we started using CloudFormation's auto-scaling rolling update policy. We found some issues with that where we needed to be very careful about when exactly tasks were being terminated, were being stopped. And we have a few different iterations through that. We wrote our own Ruby script to go through and do instances one at a time. But that was taking 10 hours to do a 100 instance cluster. And you can imagine an engineer sitting there for 10 nail-biting hours watching, making sure that all the tasks are moving across safely. And we're replacing one instance at a time. So if something went wrong halfway through that process, we've got a cluster with half new instances and half old instances. And the only way to roll back is to create, again, all of the old instances. And there's some nervous moments involved in that. So what we started at the beginning of this year was Project PRISM, which is really aimed at getting that 10 hours down to less than an hour. So PRISM stands for Project Replaced in 60 Minutes. And the goals of PRISM were, first of all, safety. We wanted to ensure that there was zero downtime for applications, that while we're replacing all of the infrastructure within that cluster underneath all the applications that are running, We want to make sure that they don't experience any downtime and that it's seamless to our internal users and our external users. The other aspect, the other goal was speed. So yeah, we wanted to complete it as fast as possible. Less than an hour was our goal. We wanted to be rollbackable, so we wanted to be able to quickly retreat back to a known good state and not have to roll back by rolling forward. And we wanted to be idempotent, so if anything went wrong during this process, or if the script timed out, or something unforeseen happened, that we could just resume by restarting the script and it would pick up from where it left off. And avoid this thundering herd scenario that we had with the original approach, where as you're terminating old instances and those tasks are moving, they're moving on to instances that are just about to be replaced as you're rolling through one instance at a time. So we wanted to avoid that scenario. And we wanted to also avoid a scenario where, as we're going for speed with replacing all of these instances and creating new containers, new images, we wanted to make sure that there wasn't a big burden on our internal Docker registry where the images will be pulled down for, and likewise a big burden on our internal network while all of this image copying was taking place. So we split PRISM down into 3 different phases, each of them independently rollbackable and idempotent. The first phase was called expand, the second relocate tasks, and then the third was to clean up. So in the first phase, we took this cluster that we showed before, and we duplicated the CloudFormation stack, which created a new auto-scaling group with all of the replacement instances. So if we had a 100 instance cluster, we would create a duplicate stack with the 100 new instances running on the new AMI that we'd built. And those 100 instances at launch time would join the ECS cluster. And it was quite amazing to see within 6 minutes, 100 new instances join the cluster. And then phase 2, we took advantage of the draining feature that the ECS team introduced last year, which was very beneficial. And what the draining feature does is you set an instance into draining mode, and that says, all right, ECS says, all of the tasks that are running on this draining instance, they need to be relocated to an instance that's not draining. And so it won't stop those tasks on the draining instance until they're safely running on other active instances and behind the respective load balancers for those services. And so that was a big win for us. So what we do is we go through in batches of instances in the old auto-scaling group. We set them to draining, and we programmatically poll, waiting until a certain threshold of tasks has safely moved, and then we'll move on to the next batch. And once those instances are fully drained, phase 3 is to clean up by just simply removing the old stack. So there were a few benefits of this approach, and one of them was the ability to roll back. So at any point in time, if something went wrong on the new stack with the relocation, we could simply reverse the draining process, set the old instances into active mode, and then set the new instances into draining, wait for them to retreat back to the known good state that had been running in production for a while already, and then we could just terminate the new stack, and we didn't have to wait a long time for that to happen. So for a 100 instance cluster, which is what we saw at the beginning of the year for 10 hours, for the old process, we reduced that to around half an hour. So it actually worked out to be really good. And then after phase 3, you're left with just a single stack running on the new ECS cluster. So another aspect of this is monitoring of our clusters. So ECS doesn't provide monitoring. You need to set up your own monitoring dashboards and alerts. They do provide some CloudWatch statistics that you can use and can take advantage of, but you still need to be very aware of what's going on in your clusters. So this is a monitoring dashboard we have in a tool called Grafana. It's a popular open source tool. Each row is a different region. So the top row there, you can see that we're monitoring CPU and memory utilization and reservation, which is a statistic we get at the ECS level, an average across the entire cluster. We're monitoring the number of instances in the auto-scaling groups, and we're monitoring instances, services, and tasks within that same cluster. The things that by experience that we've come to learn to monitor is memory, CPU, disk for just about everything. You want to know about any issues going on in this before your internal users do. The clusters themselves, as I mentioned, have some statistics that you can keep an eye on. Auto-scaling groups, watching those statistics. The build and deployment servers, don't forget to monitor those, what's going on, because your teams, we treat We treat our test environment internally. We're responsible for maintaining the test environment and making sure deployments are smooth. We want to make sure that our internal users' experience is just as smooth in test as it is in production. So if there's any issues in test, we want to treat that like it is production internally for our team. And similarly for our Jenkins build nodes, logging servers, Docker registry, these are all the things that we've come to learn. It's really important to keep an eye on those things and know about problems that are going on there. So what does it look like in terms of how do the metrics get into our Grafana dashboard? So we've got our EC2 instances in our autoscaling group, and each instance will be pushing metrics to CloudWatch. So I mentioned those custom metrics that we have. So we're checking the state of the ECS agent and the Docker daemon, periodically pushing the state whether they're running or not, so we can alert if it's been down for some time. We push extended CloudWatch metrics using the standard CloudWatch scripts, and we've got some cron jobs that push some other custom metrics as well. And then our Grafana dashboard is able to pull down those metrics from CloudWatch directly. Then we use Jenkins to periodically pull down some stats from the autoscaling group itself just by querying the Amazon APIs, push those to Graphite, which is another common open source monitoring tool, and Grafana pulls in those statistics from Graphite. And we've built in some chat room integration with Slack, so we get notified about any alerts that are going on or autoscaling events or various different things. We keep an eye on the channel and make sure things are going smoothly. And then when it comes to right-sizing instances, this is a tricky aspect of cluster management. What you want to go for is a balance between your CPU and your memory statistics on your instances. So you want to make sure that you've got the right mix there. We started off with C4 4x large instances, but we found with 30 gigs of RAM, 16 cores, we found that people were not using much of the CPU that they had reserved. So we changed our default CPU reservation for applications that are generated by Primer. We set that down to 1/8 of a core. And then we changed our instance type to R4 2x large, which gives double the memory and half the CPU. And I showed this diagram before. This cluster is at about 64% CPU reservation. It will be somewhere between 60 and 75%, depending on how many autoscaling events are triggered. But still, we're only at 12% CPU utilization. For memory, we're at around 30% reservation and around 13% utilization. And you can see that we've got the instance type right in terms of memory and CPU are around the 12-13% mark. So we've got the right size of the instance type to utilization. But when it comes to reservation, we need to work more closely with our teams to say, you're reserving a lot of CPU cores that we're just not using, and it's up to us to go back and socialize and try and get that balance right across the org. So in terms of cluster management, the benefits that we get out of this approach, this investment that we have, we get the speed out of having those pre-built ECS clusters, which means that there's no EC2 instance startup time for deployments or for autoscaling, because we've pre-built those clusters and they scale out independently of deployment and autoscaling activities. Another aspect of speed is that when you build a Docker image, if you have two Java applications that were both built off the same base image, then when it comes to pulling down that application image to an instance, if an instance is running two totally different Java applications, they can share the same base image. And that base image only needs to be pulled down once. And then for the second application, it just needs to pull down that extra layer on top with the artifact for that image. So that's another benefit that we get out of having a shared ECS cluster or any sort of clustering technology, is that Docker can take advantage of the fact that it only needs to pull down the differences in image layers. We also get safety aspects out of this as well. So because we're using the immutable server approach, it means there's no configuration drift from one instance to another. We're never asking the question, why is this instance misbehaving? What's somebody gone and done on that instance? Why is that instance different to any others? We just simply accept the fact that at scale, you're going to have problems that you can't foresee. You simply terminate the instance and you can investigate to see, is this going to be a widespread issue that we have? But it just reduces a lot of the questions that you have around what are the potential changes that are going on between different instance types. And the last benefit there is scale. So because these clusters automatically scale horizontally to match, we're hands-off. We just we let autoscaling take care of that. So we start off with a 5-instance cluster, and then we come back and it's at 30 instances because teams have been deploying to that region. Our big clusters, they just keep scaling bigger and bigger. So people ask us, what sort of skill set do you have within your team that supports this? We have around 8 people that take responsibility for those middle 2 aspects. So our cloud acceleration team, it's a worldwide team. And within our Brisbane office, we focus mostly on these aspects here, but we'll also contribute to the wider cloud effort. And there'll be people from other offices that also contribute. So this is a virtual allocation of people that we need to keep this platform running. And we have about 6 engineers with different development and operations backgrounds, myself as engineering manager and a project manager. And what we do is we liaise with the Amazon ECS team if there's any issues, if there's any feedback that we have, or if they have recommendations. We do that upgrading of ECS clusters, so periodically we'll go through and replace the clusters with new AMIs. We're assisting development teams with their questions about how do we get into the cloud, monitoring of those AWS resource limits that you need to be very aware of, cost optimization, monitoring infrastructure, migrations. We kind of sit as this team in the middle, the cloud team between Amazon and our developers. So we're really trying to accelerate the developers' experience. So when it comes to what the developers have to do, well, they're the ones that go into Primer and create their microservices. They're responsible for configuring their pipelines and configuring their build jobs, and configuring their applications. And then we're responsible for building that platform in between. And then we liaise with Amazon. So they're responsible for the ECS scheduler, that brain, the central brain. We don't get involved in that. We just, if there's any issues with that, we will just contact them. And then that does the scheduling of tasks, and then we get involved in recommendations and feedback about the service itself. So what are some of the lessons that we've learned along the way? The first one is monitoring is your friend, and we learned this the hard way. So I come from a development background, and we quickly encountered just issues where maybe we weren't monitoring CPU and disk. So we were, in the early days, surprised by things that developers would tell us about. So really appreciate having some good, strong sysadmin skills in the team now, and they've been helping us to really solidify that experience. Next is true blue-green deploys. So I mentioned before how we do blue-green deploys is by having a Canary service. So we do a separate deploy to release process. And some of the issues that we've experienced with this process is that you can't easily roll back without re-releasing. If you want to go from V2 to V1, you have to roll back by re-releasing V1 and testing tasks independently there. The other issues is that some aspects of load balancers are immutable. So if you want to change your ELB scheme from internet-facing to private to internal, you can't do that. And you might want to create a whole new load balancer for your service, but ECS has a one-to-one mapping with ELB that you can't modify after you've created your ECS service. So any of our internal customers that want a new load balancer, we have to say, well, you have to create a new service, or you have to experience some downtime for your app while you replace it. So that's some of the aspects there that we see. So the true blue-green approach is, this is what we actually use for our dedicated EC2 platform that we have. And we want to move our ECS deployments over to it as well. And what we do there is we treat the live service, the version 1 service, as the blue stack. And then when it comes to upgrading to version 2, we'll create a whole new load balancer and a new ECS service as the green stack running version 2. So instead of a single Canary task, we'll create all the replacement tasks with a whole new load balancer. And the idea is that we would test against the load balancer direct. And then when it comes to release time, we would send traffic from the old load balancer to the new load balancer. And we can bleed that traffic over across slowly. So you can start off with 10% and just do some load testing. If you're processing thousands of transactions, you can just see how are we going on version 2 with the 10% of the traffic. If there's an issue, you can roll back to 100% on the old version. And it allows you to have new ELB settings, but you do have to warm up that ELB, so that's why we would bleed the traffic over gradually, and it's a tweakable thing that users can choose at deployment time, at release time, how quickly they want to roll over to the new load balancer. So eventually you'd be sending 100% traffic to the load balancer. If there's some issues with version 2, you can simply roll back to the old load balancer with a CNAME switch. And once you're happy, you'd go back and send all of your traffic. All would be running on that version 2. The next lesson is to know your limits. So in terms of resource limits, the number of services you can have per cluster is 500, and we did hit this limit. The solution is to ask nicely, and the ECS support team can increase it for you. Some changes that can't be made that we've hit is when it comes to the registration rate for ECS agents connecting to the ECS scheduler. So with our PRISM project, we were trying to stand up those 100 replacement instances all at once. And so we have 100 agents trying to, all within the same couple of seconds, register into the central brain, and would get some API rate limit issues there. So we solved that just simply by having an exponential backoff in our ECS agent startup script that I mentioned, that we control when to start up that ECS agent. The other limits to be aware of is rate limits when it comes to API rate limits. Now, what we experienced as our accounts and our clusters were getting bigger and bigger, the more ELBs and the more ECS services we have, the more chatty those two services are on our behalf to each other. So what we're working towards is sharding our accounts into smaller accounts, which I think is the recommended best practice. We're looking at each large team having their own account. We take advantage of CloudTrail events, and we'll push those events into Elasticsearch, and then we'll use Kibana to visualize, which is an example there, which really helps to drill down. If you're experiencing API rate limits, go and see what are the biggest offenders by analyzing your Kibana visualizations. Another lesson that we learned is to avoid autoscale thrashing. And by this I mean the problem where you scale up due to perhaps CPU reservation being too high and the cluster needs to expand, but then 5 minutes later it realizes that memory utilization memory reservation is too low, so it will scale back down, and it repeats that cycle over and over every 5 minutes. So the way to fix that, there's a few solutions. You can fix your scaling dimensions so that you only scale down when both are low. To do that, you need to create your own custom CloudWatch metric, which combines CPU and memory, and push that to CloudWatch and only use that specifically when you're scaling down. Another solution that you could have for that is to fix the ratios at which you configure your services. So if you have an 8-core and 64 gig instance type, which is like a ratio of 1 to 8, make sure that your users can only have a 1 to 8 ratio when they're specifying the memory and CPU statistics for their application. The solution we ended up with was just, for now, set the scale down policies low. We rarely need to scale down anyway because we're just organically growing as more and more primer applications are being created every day. Some of the future plans that we have in place, or that we're looking at doing, some things that we'd like to get on top of is cost allocation. How do we allocate costs to individual teams when we're having this shared infrastructure? A service discovery approach, particularly for internal private applications. Moving towards ECR gives us some extra redundancy, having an ECR per region. So to summarize, the benefits that we get out of this microservice platform using ECS, we've got the primer application, the primer tool there, which gives us the benefits of reduced cost of experimentation and that fast feedback. The deployment automation gives us that speed and safety when it comes to reducing a lot of manual steps down to repeatable, reliable steps at the click of a button or fully automated. And then the cluster management, the investment we have there in keeping those ECS clusters maintained, it means that we've got those pre-built instances there ready to receive Docker workloads and giving the ultimate speed at deployment and auto-scaling time. And also the sharing of those Docker layers that I mentioned increases the speed, the immutable server approach, no configuration drift, and the ability to auto-scale horizontally. So that's just to summarize the benefits we get. So did we succeed? I mentioned that our mission as a cloud acceleration team is to speed up developers' lives, to make their lives faster and easier. So our hypothesis was, going back 2.5 years now when we embarked on this journey, we thought that we could make developers' lives faster, maybe double the speed at which it takes to deploy using Docker instead of dedicated EC2 instances. So our initial primer approach did use Docker EC2 instances, and that would use Chef to build AMIs, and it would take about 30 minutes to deploy because it needs to spin up a new instance, it needs to pull down Chef, set up all the configuration and software, and it needs to burn an AMI and then create a CloudFormation stack. For our 2.0 approach using Docker with ECS, it takes 3 minutes to do that process. And this is just talking about the initial deploy to the initial testing environment, so to get production-like feedback. So we receive that feedback as a developer. Every commit, you'll receive that feedback 27 minutes faster because it takes advantage of having that shared ECS infrastructure. And our developers do, on average, 524 deploys per day, per business day, to our initial testing environment. So if you multiply that out as you go further right, you'll see that 524 times 27 minutes, that's a saving of about 29.5 business days every day. So that means that our developers will receive that feedback. And this is the most critical feedback, right? It's the, will this commit that I've made, will this change I've made actually work in a production-like environment? So just that initial commit and deploy. So that's, it's pretty staggering when you kind of look at the figures and say, well, because we're deploying a lot faster, we can do a lot more deploys, and because we're doing that, we're saving a lot of time. And that's with a support team of around 8 people, we save around 30 developer days every day. So using these pre-built fleets of ECS instances with these clusters, we were able to speed up deploy times and be able to quickly and safely deploy software as Docker images. And this has effectively reduced that opportunity cost by a factor of 30 times. And together with the Primer microservice generation platform, it really helps to capture that time value of information and bring that experimentation down and get that feedback as early as possible. So we have some time for questions now. There's some microphones set up either side of the room. So any questions, please come ahead. Yeah.
So your developers are spinning things up, and so a lot of that is going to be abandoned stuff, and
Yep.
some of it, new stuff is going to come on that's going to replace older stuff. So how are you finding the stuff that's end of life and the stuff that is abandoned?
Sure. So we have around 4,000 Primer applications, and we have, in total, there was 6,500. So 2,500 have already been deleted. There are temporary experiments. And it's really up to each individual team to decide what that life cycle is. So we will find some apps, some applications that are abandoned, that are kind of running still in our clusters. And we'll usually go through and contact the authors and say, hey, did you know this was still running there? And that,
so that really requires people just looking,
yeah.
seeing in the analytics, knowing it.
Yeah. Yeah, the question there was that requires people looking at it and seeing, is this still being used? Yeah, that's the case, yeah.
This is really inspiring work, I must say, because we're trying to get this far in my organization. My question is, some of the capabilities are provided by the platform, like auto-scaling and so on. How much local development, software development, did your teams need to do in order to realize this full end-to-end solution?
Sure. When it comes specifically to auto-scaling, this is where we fully take advantage of the features that are in the AWS platform for auto-scaling. So the only automation that we need to write is to configure at deployment time for the applications to say, all right, create some CloudWatch alarms for this application, and tell the ECS service that when you're deploying this service, use these CloudWatch alarms, and we specify the auto-scaling metrics to say when these CloudWatch alarms are fired, then spin up another 2. So that's something that we took advantage of.
Auto-scaling is one thing, but
Yep.
the whole Primer application must have been locally written, right?
Yes.
Looking past Primer into the CI/CD and throughout the ability to do the blue-green deploys, how much of that work, what were the biggest challenges that needed to be solved in software?
Yeah, it is a significant effort that we've invested internally. So Primer started in 2014, with an idea that, hey, if we can automate all this stuff, it will make people's lives easier. And then from there, once we built it, people came, right? So people started using it and were quite surprised at how popular it became. And from there, it's a matter of, it's kind of almost in an internal startup mode, right? You build something, you've got an experiment, and then people start using it. And so you need to start building in more safety, you need to start building in more automation and smoothing out the developer experience. And as more and more people internally within the company start adopting it, that's where you need to start investing more and you get more buy-in to have the internal resources come and work on it. So we have a number of different internal services and internal teams. Some people working on the Primer UX aspect, the Primer tool. Some people working on the cluster management. Other people working on account management and different aspects. So,
I see. Thank you.
Yeah, great.
Hi. For your blue-green deployments, you mentioned that you're able to tip a certain percentage of the traffic to the
That's aspirational, but it does exist on our other.
Okay, yeah, I was going to ask where exactly you turn that dial.
Right. Yeah. So the logic behind that. So what we do at release time on our EC2 platform that we want to move to our ECS platform. At release time in your Jenkins build, you can say, I want 10% traffic at a time to be bled, and I want this whole bleeding process to take 5 minutes. And so it's a simple math calculation to say, okay, well, do 10% and divide that across 5 minute interval, 5 minute entire period. And so what will happen there is, the way it works is with Route 53, with weighted CNAMEs, we'll start off 100% goes to the old load balancer. And so I think we just use the figure 100.
And then, so Route 53 feature.
Route 53 weighted CNAMEs, yeah. And then so we'll reduce that to 90 for the old load balancer and simultaneously 10 for the new load balancer. And then traffic starts going across 10%, and then you just kind of do that in intervals, yeah.
Hi. I had a question about secret management.
Mm-hmm.
So you mentioned application configurations. How are you guys doing it? What's best practice there?
Sure, yeah, and that's up to each individual team internally to work with the security team, and they work out where secrets should be stored and the appropriate process for that.
All right, so it's application specific.
Yeah.
It's not something you guys manage.
No. Yeah.
All right, thanks.
No problems.
Hi. So we're doing a fair amount of the stuff that you're doing, but at the moment, instead of using Primer, we just sort of copy and paste things, which has worked well-ish, but we're starting to get to the point where it's not really going to cut it anymore.
Yeah.
Could you talk just a little bit about roughly how Primer is set up?
Yeah. Yeah, sure. So it started its life as a series of Python and Bash scripts, and the templates were just Git repos, one per template. And it would take the template, bring it down from Git, apply some parameterization to it, like change the app name token, and then push it to a new Git repo for that application. And now it's more advanced. We use a series of services that we've built up, and we'll take in different templates, but the underlying concept is still there. One Git repo per template, and then pull it down, parameterize it with the correct values. And so we'll bring in metadata from different places for the application. And it really started off as a community effort. So when it comes to maintaining those templates, it relies on the community to do that. And then we try and make that experience as consistent as possible across the different applications. Yeah.
Just a specific follow-up, I guess. As a maybe simple example, some applications need databases and some don't. So do you really just have a template for every commonly used combination of technologies?
Right. No, we don't do that. No, we leave database choices up to each team how they want to do that. Yeah. But then we do provide some self-service tools to be able to create those resources as well, but each team's responsible for what back-end choices they want to make. Yeah.
Thanks.
No worries.
Hi. We struggle to get our developers to rebuild their containers when there's security patches Only when there's critical can we really force them. How
Right.
do you deal with that on a large scale?
Yeah, that's right. We've got to get it out there, and I think at deployment time, that's where you can really say, no, you can't deploy anymore because your container is using an older version. Yeah.
And they let you get away with that?
Yeah, yeah.
Okay.
That's right. We've got time for a couple more questions if there's any. Otherwise, we can get an early mark and get ready for the next session. Oh, we've got one again.
I guess I got one more. So you were talking about bringing down the deployment time from that 10-hour nightmare to getting it within an hour. And part of that was the item potency where you were able to roll it back. So I guess I don't have much of a question as much as I think is I'm dubious about that.
Right.
Like, so if you have a change, right, and you have some asynchronous process going on, maybe somebody's going on a queue or something like that, and you've had a change in the code coming in, and then you're running the task, you run it over on the new stuff, and then you roll back, and the old stuff may end up getting unexpected data or not data that expects it's not there. So you're still gonna have to jump in there and do something, do some recovery, right? I mean, does that make sense? Am I misunderstanding something?
Yeah, I think I'm understanding you. So the rollback, is specific for a certain category of issues. It won't cover every issue.
Right.
The issue that it's designed to capture is when you go from an old AMI to a new AMI, things look good when they're starting to relocate, but then perhaps after a few minutes you realize there's just not something that's not quite right with the new AMI. Maybe it's a new version of Docker or something in that environment's not quite right.
So this is not necessarily like a business rules change or logic change or anything like that. This is, okay, all right, yeah, that makes a lot more sense. Good.
Yeah, and then so that being able to retreat back to a known good is in most cases going to satisfy the problems that you're trying to recover from.
Yeah. Well, I love what you've done, and you explained it really straightforwardly. I appreciate it. Thanks.
Great, thanks for the feedback. Appreciate that.
Quick question, you get an
Yeah.
open source primer by any chance?
That question comes up a lot, and I've heard that a lot of companies have their own internal primer. It has been talked about internally, but yeah, I can't comment beyond that. I don't know. Yeah, yeah. Great. Well, thanks for coming, everybody. Enjoy.